We have Younghoo Lee and Joshua Saxe from Sophos, and the topic today is GPT-3 and me, how supercomputer-scale neural network models apply to defensive cybersecurity problems. Please welcome Younghoo and Josh.
Okay, everybody hear me without straining to understand what I'm saying? Yeah, okay, cool. I'll try to talk close to the mic, which is a little awkward because I'm tall. Okay, oh, the other thing was, there's a laser pointer here, isn't there? But remind me what button? Oh, yeah, oh, awesome. Okay, that's great. Okay, so I'm here with Younghoo Lee. We're going to co-present here, and I want to say thanks to Younghoo. He flew here from Sydney in the last 20 hours and just arrived like an hour ago. So yeah, happy he got here on time, and looking forward to presenting together. So our talk today is entitled GPT-3 and Me: How Supercomputer-Scale Neural Network Models Apply to Defensive Cybersecurity Problems. A little bit about us. I'm Josh Saxe. I'm chief scientist at Sophos. If you like what you hear today, you're welcome to check out our book, Malware Data Science. I wrote this with Hilary Sanders. It's about malware data science and security data science more generally. I've been doing cybersecurity machine learning research for a long time now. Younghoo, you want to introduce yourself quickly?
Yeah, good afternoon, everyone. My name is Younghoo. I'm a senior, recently I'm promoted. I'm principal research scientist. Yeah.
Okay, cool. Thanks, Younghoo. Okay, so I'm going to lay out right off the bat the main arguments of this talk. So first, and those of you who came to my morning talk, you heard me hint at this a little bit. I think two ideas that are new/gaining popularity in machine learning, self-supervised learning and model scale, are fundamentally changing machine learning and what its capabilities are. And I'm going to talk about the implications of that for security today, and so is Younghoo. Second, I think that for those of us who are security data science researchers here, I think a new important topic on our research agenda should be figuring out how large models apply, large self-supervised trained models apply to security. I think that's a problem for us to figure out over the next 1, 2, 5, 10 years. And hopefully I'll convince you of why, and so will Younghoo in this talk. Third, I think the proof of concepts that Younghoo is going to show that are built on large language models, and specifically GPT-3, really show promise, really prove out the thesis that large models are going to be important for our field. And then lastly, this is not so much a thesis, it's just a caveat. What we're presenting here today is early work meant to whet the appetite of our community around the potential impact of large models. Let me ask, how many of you know what GPT-3 is when I use that acronym? Okay, so I'm going to use that. Not everybody raised their hands. So this is a kind of iconic large machine learning model that's been built by an organization called OpenAI. It can't be run on commodity systems. You need like a very large supercomputer to run this model. But it's showing some really novel capabilities with respect to natural language processing. And you'll learn more about it in the course of this talk. And then finally, by way of just summarizing what we're going to say up front at the beginning of this talk, Younghoo's going to demonstrate a couple key results in our research. First, he's going to show that experiments we've developed at Sophos, where we both work, demonstrate that GPT-3 can do something fundamentally new, which is successfully execute a small reverse engineering task, which is to take command lines like this, which SOC analysts at Sophos and many other places spend their days looking through, and translate them into clear and accurate natural language descriptions like this description on the right. So here, I mean, if you just sort of introspect and notice the cognitive load of trying to parse a command line like this, you'll notice that even those of us who look at a lot of command lines like this, it takes some exertion to figure out what they mean. And it's significant that we found a method for using a model like GPT-3 to translate that into clearly written text, which explains what's going on. And if you imagine the job of a SOC analyst is looking through hundreds of these suspicious command lines a day, it's significant that a large language model can be put to use in translating that into intelligible English. The second result that Younghoo's really going to deep dive into, which I think is really significant, is in a context in which you have very few training examples. So let's say you are attempting to detect phishing emails on a customer network and you have just a handful of benign examples and a handful of email examples from a malicious campaign. We can use GPT-3 to achieve a deployable level of accuracy in detecting other malicious emails. So Younghoo's going to drill into this more deeply, but basically we can achieve on an accuracy metric like F-score, we can achieve like a 0.9 or 0.95 result with a tiny handful of training examples, whereas traditional machine learning just is a non-starter here. It achieves a non-usable detection accuracy. So really these two key results are meant to provoke interest here and applying large language models to defensive cybersecurity problems, and I think suggest that more investment in this space is necessary, and I think are significant in their own right in terms of what we're building in our data science program at Sophos. Okay, so the format of this talk is I'm going to give a bunch of background into large models, and then Younghoo's going to drill into the examples that I just talked about. Okay, so here's an important trend, got this from the website Towards Data Science, which tracks a bunch of interesting metrics. There's a sort of meta-analysis of the scientific literature in machine learning. And what this plot shows is that over time, so on the horizontal axis we have time here, machine learning papers are proposing larger and larger models. And this was sort of a log linear relationship between time and model size for a long time. And now all of a sudden, we just have this explosion in large models being proposed by researchers. So just hang on to that fact that models are getting larger and they're getting larger at an accelerating rate. And then I want to point, and I'm going to come back to that, but I want to point to another trend here as well, which is we're also seeing these models being trained under a newly popular regime, which is the self-supervised regime. So self-supervised learning I'll get to in a second, but basically its reason for being is that it helps to exploit the internet scale data sets that are becoming available to machine learning researchers. So you have this nonlinear trend in the amount of data that being generated by computing devices and available on the internet. Self-supervised learning helps solve the problem for machine learning researchers, which is that most of those data are unlabeled, so we can't use traditional supervised machine learning approaches to take advantage of them. And self-supervised learning allows machine learning models to improve even while they're unlabeled. So here's what self-supervised learning is. So basically, what a self-supervised learning approach does, it takes unlabeled data and creates a kind of artificial prediction task on that data. So for example, one approach to taking advantage of large image data sets where we don't have prediction targets, where we don't have, say, labels that say, this is a picture of a primate, is you just create a game, right? Like remove a patch from the image and then have the machine learning try to fill in the pixels that we've removed. And then just repeat that over and over again for a given image. So remove a patch here and predict it, remove a patch here and predict it, remove a patch here and predict it. And by training a machine learning model on web scale image data sets to solve this sort of artificial task of filling in the missing pixels, it turns out that the model learns useful representations of images. Because if you think about it, to solve the problem of predicting the missing patch here, maybe this is a better example, the primate's face. The model really has to learn a lot of useful semantics around what images actually mean. It takes, to really solve this problem of knowing what those pixels will look like, means understanding what an ape's face looks like and inferring that the relationship between the body of the ape here and the pixels in the ape's face. And it just turns out that a model trained in this way on self-supervised data can then be used downstream to solve image classification problems, for example, better than a model that just that wasn't trained in that way. Okay, now, so we're getting all these models that are very large and trained in a self-supervised fashion outside of security. Today's security data science models really live in this kind of size range. So on this axis, we have size expressed in parameters. The models we deploy within the data science team that I manage at Sophos are all really within this range. And that's notable because what's happening in the research community outside of security is folks are finding that these models in this much larger size range are more efficacious. So this raises the question, how can we take advantage of self-supervised training and large models and web scale data in order to get the boost in results that researchers in the image domain and the audio domain and the language domain outside of security are getting? And so, that's what this talk goes towards is, we are experimenting with GPT-3 in this talk, which is about this size. So it's really up there on the vanguard of model scales in terms of models being used in the machine learning community. So I want to dramatize just a little bit more what I mean when I talk about large-scale models trained on self-supervised learning tasks getting better results. So here I'm going to show some results from a model trained by a team at Google. This is called the Party model. That's very large scale and was trained on like a web scale image data set. So what this model was trained to do is was given an image caption, like the alt text that you find in images on the internet, predict the pixels in the paired image. So here we've got the caption, a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses standing on the grass in front of the Sydney Opera House holding a sign on the chest that says welcome friends. So to be clear, this image doesn't actually exist on the internet. What these researchers were trying to do with this sentence is see whether or not the model had learned so much about the relationship between text and imagery that it was able to generalize and create a convincing portrait of a kangaroo with all these attributes and the Sydney Opera House in the background. Now, here's the interesting result, right? So this model was trained in this self-supervised way just to predict, play the game of predicting image pixels based on their alt text. And with a model at the scale of 350 million parameters, and this is about, 15, 20 times larger than any model that we've deployed within Sophos products, it was able to do like a pretty decent job, right? I mean, this looks sort of kangaroo-like. It's got the sunglasses in there. It's got a sign. It doesn't have the welcome friends text on the sign, but there's some letters on it. It's got a vague visual gesture at a hoodie. It didn't really solve the problem, but it's impressive nonetheless. Now, if we scale up to 3 billion parameters, it gets more interesting, right? I mean, this is unmistakably kangaroo-like. This creature here. It's got the sunglasses, and the letters are actually getting closer to what the researchers asked for, which is welcome friends, right? This is remarkable. I'll just say, even at this level of success, right? That the fact that a model merely trained to predict an image based on its alt text actually learned to write, right? It actually learned to write some letters all on its own, which I think is really remarkable. But still, I mean, we're still pretty far off from completely solving the problem. Now, once we get to 20 billion parameters, I mean, this is at the scale where you'd need to fill up this room with a distributed sort of GPU setup in order to run a model of this scale. The model solves the problem. So here we really do have a kangaroo with blue sunglasses. The model has learned to write out welcome friends on its sign, and you've got the Sydney Opera House in the background. And what's noteworthy is that these capabilities just emerged from the model playing this game of predicting the pixels from the alt text, right? Additionally, what's noteworthy is that the researchers here didn't introduce any clever new mathy ideas into their model as they scaled it up. The model, just by virtue of the fact of having more sort of connective tissue between its artificial neurons, just gained these capabilities. Just gained the capability to write, and it gained the sort of memory of what the Sydney Opera House looks like and what kangaroos look like, and also learned to sort of compose all those concepts together in an image. I showed this in the talk I gave this morning, but just another example. So that same model, given the prompt, a map of the United States made out of sushi, it is on a table next to a glass of red wine, right? It doesn't do well in a low parameter regime, but as you just scale it up without changing anything else, learns to create a map based on, with sushi and the wine glass, and learns to put a table in the background. So this is really significant, I think. It's significant for machine learning that we can now prompt models with natural language text and generate coherent imagery that really aligns with the semantics of the text. But I think the question we should be asking ourselves as security practitioners is, how does it apply to security? And the question that Younghoo and I are asking ourselves is, how does it apply specifically to the defensive problems in security? I think it's easier to see how it applies to offensive security. Like if you want to generate fake social media content or fake Facebook profiles, right? You can use models like this to generate that kind of content. But how do we use it in the SOC, and how do we use it when we're defending real networks is the question that we're asking here. I want to say by way of summary, I'm showing sort of qualitative results around what happens when we scale models up. This very famous paper that came out a few years ago, Scaling Laws for Neural Language Models, it came out of OpenAI, shows this really beautiful relationship between scale and error rate. So here, they're just showing this is what's called a power law relationship between model error when it comes to, in this case, they looked at predicting the next few characters in a document based on the characters that the model has seen so far. They're able to show that the error rate of models that are doing this autocomplete problem just goes down in this really smooth fashion as we just merely scale up the size of models. And this is a robust result that's been shown in a number of different domains. So to sort of hone in a little bit more on why this matters for cybersecurity, here's an experiment I did with the GPT-3 codex model, which was trained on lots and lots of code, like GitHub scale code from the internet. So I wrote out this Python function signature and docstring. So the function is called compute mean and standard deviation. So there's two standard summary statistics and stats. And then the docstring says compute mean and standard deviation on the input data in pure Python and render the result in flashy HTML on a page titled "Don't Trust Summary Statistics." And then the GPT-3 autocomplete wrote the code correctly, which I think is interesting because it's sort of like the kangaroo example in that if mean and standard deviation are the kangaroo, and the HTML part, don't trust summary statistics is the hoodie, right? The model sort of knew both of those concepts and composed them together in a function that will actually execute and do what I asked it to do. So we can see that these large models also can understand the technical domain of Python code when they get to a sufficient scale. This model is about 200 billion parameters in size, so very large and has very, very high capacity. And then I apologize for folks who were in the morning talk. I sort of foreshadowed this, but here's an example of using GPT-3 to classify domains. So here I gave GPT-3 the prompt, Berkeley.edu maps to education, Amazon maps to shopping, Netflix maps to entertainment, etc. And my goal was to get it to classify a new domain that it had never seen before accurately, just based on the 5 training examples I gave it in the prompt. And so I gave it this new example, shootingrange.com, and asked it to complete the pattern, and it gave weapons as the answer. And I think that's really significant for security, because let's say there's practical challenges to actually do this right now, given how big and costly it is to use GPT-3, but I think it's useful to think ahead and think in a SOC, if you want to recognize new examples of a pattern that you're seeing, the fact that you can just type out 5 examples and then GPT-3 will sort of recognize conceptually equivalent content in the future is significant, right? You could write something out like this and then ask GPT-3 to go find, to go categorize all the domains that your users have looked at over the past day. And the tactical power of this over traditional machine learning, which requires tens of thousands or millions of examples, is really dramatic, right? The ability just to write out a pattern and deploy a model very quickly, I think, is significant. Here's another example of using GPT-3 in this way, where it's given security examples of good domains and bad domains, like this PayPal sort of phishing URL or this city card phishing URL, and then it's able to detect, given a new domain, that it's bad just given a handful of training examples. I mean, just to emphasize, so using GPT-3 to make detections in this way, it requires orders of magnitude less training data than using traditional machine learning. As Younghoo's going to talk about that more later, but we would need like tens of thousands of examples to get a machine learning system functioning, as well as we're getting GPT-3 to function with 5 training examples. So in context where you have just a few examples of a bad kind of observation that you need to detect, I think these large models are really significant. Now, I've been teaching GPT-3 in these examples to detect malicious observations using a method called in-context learning. And in-context learning is just a fancy way of talking about using a model like GPT-3, giving a model like GPT-3 a prompt, and then asking it to autocomplete. So here, I'm not, for data scientists in the audience, there are no gradients, there's no stochastic gradient descent, there's no backpropagation. Literally, we're just writing some text and asking GPT-3 to autocomplete and getting an answer in this way. And there's a whole body of research now around in-context learning and prompting large models in the way that I'm showing here in order to get predictions. Now, there's another way that you can adapt large language models to solve a problem like detecting malicious domains, which is called fine-tuning. And that does use the traditional deep learning optimization methods like backpropagation and stochastic gradient descent. Basically, the idea there is we use, so when we're fitting a large neural network to data, like GPT-3, we initially fit it using a self-supervised learning procedure, like predicting the next few letters of a document given the characters in the document up to the point in which we're looking in the document. We play that kind of self-supervised learning game with the model, and we use traditional neural network training, like backpropagation and stochastic gradient descent, to sort of get ourselves to a good region of the parameter space. So we're sort of tuning all of our neural network weights in that way. And then we do a little bit more backpropagation and stochastic gradient descent in order to solve a downstream task like detecting malicious domains. And what we're finding is that a combination of in-context learning and fine-tuning tends to get us the best results. Younghoo will talk more about our experiments there. Okay, so just wrapping up. So this is my last slide, and I'm going to pass it off to Younghoo. Hopefully, I've whet your appetite into thinking about the significance of these large models and their significance for cybersecurity. And maybe folks, even now or subsequent to this talk, will have some ideas about where they might apply within cybersecurity. Here are some areas that we're thinking about. So I've already mentioned, using large language models to detect previously unseen attacks better than we're currently able to detect. Clearly, interesting capabilities emerge when we scale neural networks up to the level that I've described, and I think that's an area that we can be thinking in. Younghoo actually has done a bunch of work around building capability on top of GPT-3 that translates between a natural language query, like show me all outgoing SMTP connections on my network that are connecting from our machines in Australia to machines in Belarus, like asking basically he's developed technology that allows us to ask a question like that and have GPT translate that into a structured query into a database. We've had some success there. I think that's a really interesting area. Obviously, we're going to be talking about models that help reverse engineer obscure and obfuscated code. Autocomplete on steroids models for security operations. So in cases where security operators are typing command lines, could we auto-suggest a menu of actions they might take using GPT-3? And I think there's a lot of other possible applications, but I just wanted to throw those out in a brainstormy kind of way. So I'll pass it over to Younghoo now to talk in detail about the experiments we've been doing with GPT-3. So here you go.
Yeah, thank you, Josh. The kangaroos, especially the 2 million parameter one, was very impressive to me. Especially, I'm from Australia, so it was a long trip from Sydney to Las Vegas. But it was great to meet those wonderful animals here again. In the second part of our talk, I will talk about 2 cybersecurity use cases you can apply a large-scale language model. So So actually, there's not many, but a few different large-scale language models. But we can use GPT-3 as our large-scale language model. And usually, it is too large. You can use directly unless you have a supercomputer. But luckily, we can use OpenAI's API to build a powerful application. Let me show you how you can build such powerful application. So our first application is spam detection with GPT-3. When you start a new ML project, probably you will start with few samples. So we have the same problem. We just collected 2 or 4 malicious spam samples, but we wanted to build a new spam detector with those samples. Traditional ML machine learning models usually does not work with few samples. So it's something like when you train a small puppy, probably you need to show him a lot of examples to teach a good skill. But however, a smart dog with a lot of experience, the dog will just learn quickly with few examples. So our superscale large language model, pre-trained language model, can do a great job with few examples. I will show you how we can do that. So Joshi mentioned earlier, we achieved impressive the detection accuracy with our model. So as you can see, GPT-3 with only 2 examples, one ham and one spam message, we achieved about 90% accuracy. And with some additional 8 samples, we achieved about 95% accuracy. It is really amazing. However, one of the traditional, but it's the popular random forest model. It is a tree-based model. However, with only 2 examples, you can get like a slightly better than random guessing. This is the power of a large-scale language model. So I will talk about the details. So these are our data sets for our evaluation and the model details. So teaching GPT-3 is quite simple. So when you design a large language, the language model, the architecture is quite complex. However, utilizing the big model is quite simple. It is as simple as designing a prompt data. So it can, the GPT-3 can do a amazing job. For example, so this is our example. So we are going to translate movie titles into emoji icons. So we provide some examples with a simple instruction. The first instruction, we will convert movie titles into the emoji icons, and we provide some examples. Back to the Future, and we provide the relevant icons. And the second one, Batman, Transformers. And then we ask about our question, Star Wars. So we get the correct answer. So this is really simple, but we can build a powerful application with the same approach. So this one is called like prompt designing or prompt engineering. This is the step we will follow today. So let's design our prompt for detect spam message. We start with a simple instruction. So classified message, spam or ham. This is really simple. And then we provide some examples. So here we select one spam and one ham from our training data. And then we add our test sample. So the test sample says the pre something. And then with this input, the model can easily understand what task is about. So it is the task about classify the message as spam or ham, and we provided the relevant information. So easily the model will return spam as our output. So this is a really simple step. So we will show you some other examples about the model. So from the previous, the prompt, we now tested use message. The message says, urgent something. So this is a obvious spam. So we detected this one. Our model detected spam correctly. And the next one. So Yeah, I can see, but it is not malicious. It is not detected as spam. So this is a screenshot from OpenAI's Playground website. So where you can test your input and output with some settings. So here is one of the most important things is the model. So we set the model as text DaVinci. This is the largest language model OpenAI provided for text generation. So we used the GPT-3 to detect spam messages. So this simple use case demonstrated the power of a large-scale pre-trained language model. So the next use case is more complex than the previous simple one. So we are going to generate human-readable description from malicious command lines. In previous talk, Ben mentioned about the SOC analysts analyzing a lot of malicious command every day, but it's really a hard job. So as you can see, we have one malicious command. So it is really long and it's hard to parse. So it is really hard to understand the hidden, the intention of this one. So our goal is actually we wanted to translate this one into human readable description. So our question is that can large language models like GPT-3 can make our analyst job easier by describing this command in simple language? Our answer is yes, it is possible. So you can see the description generated by our approach. So the complex one, now you can read. So it is simple. So actually the command create a file called exe.bat file, and it has some malicious content, and it execute and delete immediately. So it is one of the malicious behaviors attackers employ to avoid the detection with the file-based signatures. So we will talk about how we can generate this impressive description. So actually, GPT-3 is a family of large-scale language model, and it comes with two different versions. The first one is actually text generation version. So these models has been trained with large-scale text data, so it can write interesting stories. And second version is called Codex. So these models has been trained with a lot of public available source code repositories, including GitHub. So it can write code in many different languages, including Python, JavaScript, and PowerShell script, as well as many different programming languages. So this is the Codex is our choice for our second use case. And we already used the text version for our spam detection. So, okay, let's start with our simple prompt. So we provide a command as it is as a command section. In the second section, we provide a description, but we carefully design the prompt so the GPT-3 can auto-complete the domain. As a GPT-3 is a pre-trained language model, so the pre-trained language model is pre-trained during the pre-train step to predict next word. So as you can see, so this will guide the GPT-3 to write description about the command. So let's have a look at the result with this prompt. So now we can read the command will copy the exe binary to a temp folder. So it generates a valid description about the command. But actually, the command is malicious because it copies a system binary into a temp folder as Adobe exe. So it is hiding some malicious activity here, but it didn't catch that. So we are going to add some additional information to improve the quality. How we can do that? So our approach is quite simple. So usually those malicious commands will be detected by any sequence-based rules. And we can use sigma rules or Yara rules to detect those ones. So in this case, the previous command was detected as one of the Sigma rule signatures, and the detection name was Windows suspicious copy system 32. So the signature name itself tells many important information about the command. So we are going to use this information to improve the previous description. So let's have a look at the output now. So sorry, I forgot about the second version of our prompter. So in this case, we still use the same command section, but we add one additional section we call the tags, and we will be using signature names as the tags. So if the one command can be detected by multiple signatures, we will be add all with the comma separate string. And then we will ask GPT to write about the description. So now we have a better description. So you can see that actually the command will copy the binary from system folder to a tempo folder as Adobe exe. So where the attackers can use the binary to perform malicious activity. So now it correctly recognizes the malicious activity as well. So now we have much better description. So this case, previously we set the model as a text DaVinci, but now we are using Codex version, so which is Code DaVinci, the model. And also, as you can see, there are some other parameters like a temperature or in the top probability parameter. So when you change this parameter with the same input, you can generate multiple descriptions. Maybe it's slightly different, but our next step is we are not happy about this one, but we still want to improve further the description. So our approach is we can generate multiple descriptions from the same input. We can change the temperature or the topic parameters, and then we will select the best one out of multiple candidates. So our approach is using back translation. So back translation is, I can explain, like when we translate English to French word. So for example, hello to bonjour. It is not easily directly compared with the quality of the French word, but if we translate French to English, now it's clear. We can easily compare the quality of French by comparing the hello original one and back translate English hi. So now we can apply the same mechanism for our problem. So command is one language and description is another language. So we can apply the same mechanism for our case. So we can generate the description as we did before, and then also we can generate the description, the command from the description. So now we can compare the original command and the back translate command to select the best description. So okay, let me show you some of the examples. So this one is the overall step. So in step 1, we will generate multiple descriptions from one command using the different settings of the model. And then we will generate the command from the generate descriptions. And then we will rank description by similarity score between the original command and the back translated ones. So this is our new prompt for back translation step. So we provided the tag information and the description generated from the previous step as input, and then we will ask the model to complete our command. So this way we can generate back translated the command from the description. If the description has enough information, it should be able to regenerate the original command. And then also, if you do not provide any information as the command, so you probably get some random string. So that's why we just provided the first word as the prompt for the command. So yeah, these are some of the examples from the previous command. we now have two descriptions, the first and the second one. The first one actually did not exactly mention, but it just mentioned about temp. So it failed to regenerate the command. So as you can see, the final output was not Adobe, but it has the same command name. But however, the second one, so it mentioned correctly the temp Adobe in the description. So it can generate the original command correctly. So this way we can easily compare the quality of description using back translation step. So this is another example of our the description generation from a command. This one is quite interesting. Can you guess? And you have the answer. Actually, this command will search files in desktop folder and the server folder, and then find files containing password. Actually, it is finding your password from desktop folder. So you can easily understand what's the malicious activity about this one. So the second application also demonstrated the power of a large-scale pre-trained language model. So you can build a powerful spam detection with just a few samples, and also you can create a impressive application which can describe the complex command line into human-readable description. So actually, do you remember the title of our talk? Actually, the title of our talk was GPT-3 and me. It's our story, so our separate story. Now it's time for you to create your wonderful application. So maybe the next chapter will be GPT-3 and you. Thank you for listening.
If you guys have questions, we can both take turns answering. Yeah, please go ahead.
So like a lot of builders thing that has a URL that you change all the time, that needs to be a file, who's going to train this? Would you use the text training model or code? Because a lot of emails, man, you get 2,000 today, the URL just changes. You have text divergent. You know, your CEO is calling you, but a URL is like throw away your URL, like xyz.net. And that keep changing. And that's how a lot of things from inbox, because you have emails, so you can't detect that. So they just keep changing your account. If we're going to use this, we're using the text model, because it's not in the text, it's not a text on the email itself, but a URL link in your spam. That's directly to your payload.
Yeah.
Yeah, we also tried to detect the malicious URL with the same approach. Yeah, so you can still.
Oh yeah, just repeat her question.
I'm sorry. So yeah, the question is about the spam or the malicious message can include some URLs or some random strings. So it is possible to use those random strings to detect those ones. So we also tried to use malicious URLs with the same approach. Usually malicious string always has some random string. So for example, like Facebook, but it has some other random string. So it still works. So it actually recognizes the random string as the malicious part and it still can work.
In the examples that you explained about, so I understand that it used the GPT models, GPT-3 models for language and for code. But how did it work with URLs? Meaning it is not code and it is not a language. And furthermore, if we want to use this approach for things like, I don't know, malware detection or something like that, is there a simple or not very, very complicated and expensive way to do that?
Yeah, so I think you guys heard the question. Thanks for speaking into the mic. Yeah, I mean, I think, so I think it's really a problem for experimentation to know where GPT-3 will shine. And that said, I think my intuition is that GPT-3 and models like GPT-3 will do really well in cases in which the self-supervised problem they were trained on has sort of forced them into a really useful representation of the domain. So, like, I think the reason it did so well on that, oh, that's fun. It's funny, you guys are seeing my social calendar here. So I think you guys are all welcome to come to Top Golf later if you'd like. So I think the reason it did so well in that domain categorization example I gave, for example, is because it was trained on like a web scale text corpus, and it was forced to learn, quote unquote, that like shootingrange.com is like semantically quite similar to like firearms warehouse or whatever example I had in there. Now, if I was just to give it a bunch of like hex from some software binaries, I wouldn't expect it to do particularly well at all on that because it hasn't been trained in that way.
Thank you.
Sure. Yes, please, go ahead. We have another question.
So you showed that example that when you added the tags in, then the command was correctly classified as malicious, whereas before it didn't have the word malicious in its description. So I was wondering if you only provided the tag as a string, or also some contextual information what that tag meant.
Yeah. Go ahead, Young. Oh, I'm happy to. He just wants to he's like, why didn't we use a text description? Why did we just use the tag? So I think your question was, why are we just using a fairly non-descriptive tag as opposed to like a description that says like, so, you know, like a full sentence description that sort of is mapped onto the tag.
I guess what I'm trying to get at is that if you only provide the tag as a label, then the model adds the word malicious into the description, and it must have the intrinsic understanding of what that label means.
Right.
Is that what you work?
Yeah. So yeah, I'll answer, and then Younghoo add whatever you like. So I think the question is like, why did the model? So like, what's the model making? Like, what's the intuition behind the tag, and why is the model like? What's the model doing with the tag? So basically, what we did there is, so the intuition. So first of all, the goal of this is not to detect bad versus good. It's once you know something is suspicious, have the model unpack all the obscure sort of text in the command and give a clear English description of like what's going on. Our intuition about the tag, and this was entirely Younghoo's idea, was that if you give the model the tag and the prompt, you'll get the model thinking along the same lines that the analyst is thinking about the command, and then it'll write an autocomplete that sort of incorporates the information in the tag. You might wonder, well, can the model really understand like a abbreviated tag that's like win_susp_password? And like what we found is that yes, it seems to understand. It seems to internalize something about what that means and reflect that in the description. Please go ahead. Yeah.
Follow up from that, when you get that tag, the win_sus,
Yeah.
where are you doing the typing for like the R rules where you kind of match that to the appropriate rule and then give you that tag? Where does that take place?
Like the logic, like the rule matching logic.
Yeah, where is that? Because I still the OpenAI demo like you were using, and I didn't see the connection between where it then goes down to the R rules.
Yeah.
That's like
Yeah. Do you want to?
Yeah.
Repeat the question.
Yeah, I guess regarding the tag, yeah, we have many questions about. So actually, the reason to use the tag as our, additional information because we only have that information. So if we have, the textual description about the actual, the signature, so probably it will be better to provide those information, but we don't have that information at that time, so we just use as it is. But also mention, I show you some example like the movie title to the image icon. We just provided 2 or 3 examples, but the model can do that. So actually, during the pre-training, so we provide a lot of, not people, the OpenAI provide a lot of data to the model. So it can recognize not only those malicious command, but also it recognize all relevant information from many, because in your source code, so there will be some tag related ones as well as description. So it can recognize all those information.
Yeah. Also, I'll just say this is part of a larger pipeline in which there's, so yeah, you weren't seeing like the pipeline in which we're matching signatures against, that's just outside of the sort of scope of the research. But as a security company, we match command lines against. In this case, it wasn't YAR, it was Sigma, but rule-based systems. I don't know how many. Oh, please go ahead. Yeah.
Did you fine-tune any of your models, or were you just using off-the-shelf models here? And secondly, I'm interested how far away you think we are from super large neural nets being used in production to improve security.
Yeah.
Yeah, actually, the previous the spam and the second command line description, we only use the pure shot learning, not fine-tuned. But also we tested with the fine-tuning with spam detection. So with like about 1,000 samples, you get like about 99% accuracy with when you fine-tune the model. So you can improve the further with fine-tuning. And what was the next?
Like how long is it going to take?
Yeah. The problem is actually, so you can improve the performance, but the problem is that the model is really slow. So it is not good idea to use like a real detection problem. But as Ian mentioned, so in SOC case, we collect a lot of samples and we cluster, and then we select some represented samples. But so let's say that this one cluster has 1,000 samples, but we can select one command line and we can provide a description for that. So it will be easier to analyze that with the human readable description. So it has some value, but still, in terms of the runtime, the speed is a problem.
I'll add to that. So I think I'm agreeing with Younghoo here, basically. But like, I think that some of this stuff, like the stuff Younghoo demonstrated about the descriptions, could be used in the short term. Again, the question is volume and cost. So I don't know how much we spend. We probably spend like 1,000 a month or something on like GPT-3 based on So we give OpenAI 12,000 a year annualized right now just to do this research, and that's just us messing around in our research group, not deploying at Sophos scale where we've got 500,000 customers. Deploying at scale, all of a sudden the costs become really significant. What that means, I think, is that it's not that we can't use these models, but we need to use them in a discriminating way. A good analogy is malware sandboxes. Like you couldn't possibly run every email attachment that you receive in a customer base in a sandbox, but you use the sandbox very, very selectively in cases where you already know something is quite suspicious. In the case of the description generator, you'd only use that in the context of new, previously unseen alerts that we think are really suspicious and that have big command lines attached to it that are hard to parse. You just have to work out the economics of it. So I think it's possible we could deploy stuff like this really soon, but we could have to use it very sparingly. And then in the future, I think, hopefully costs will come down. I guess we can take one last question, and then I think we need to wrap it up.
Sorry, it's not really an exciting one, but have you tried this with sentiment analysis or with? You gave an example of...
Yeah. Have we tried it with sentiment analysis? Can you say a bit? So, sentiment analysis, so the question was, have we tried it with sentiment?
Yeah, right. NLP, natural language processing, but more with figuring out how someone is feeling or their emotions behind a post. Instagram, Twitter, something like that.
So in case anybody didn't hear, the question is, have we tried this in sentiment analysis? Like, so if you have a document, you categorize that document in terms of the kind of sentiment reflected in it. I don't know.
I haven't tried any, those use cases because I can only use our money to cybersecurity applications. So we only have monthly $2,000. So it's a joke. And anyway, so you can find the example from the OpenAI website. So there's one example about sentiment analysis, how you can do that. Yeah.
Well, I think we're out of time. Thanks for your questions and comments, everybody. Much appreciated.